let's get back to oscillations. And let's extend our analysis to consider systems where you don't have a single oscillator, but you have many oscillators. Or actually, let's take a continuum of oscillators. So we actually have a spatially extended system where you think of a chemical system, actually. There are many chemical systems where when you pour together the reactants, then they start to react in an oscillatory fashion. And at different locations in the Petri dish, the oscillation can have different properties, or not properties, maybe it's a different phase or a different amplitude. And so we have oscillations in a continuum system. And so let's see what we can do there in terms of nonlinear analysis and capture the dynamics in that system. So questions that arise are, well, if you have this continuum of oscillations, will they be synchronous? Or will there be maybe traveling waves, standing waves, whatever? Or are they actually stable? I mean, maybe there exist waves, but they're not stable. So those kind of questions we'd like to address. Let's take, just like in the steady spatial pattern case, let's take a system that's reflection symmetric and spatially translation invariant. And we also assume that we have constant coefficients in time. Okay, so that means we have, as I said, so we're looking at spatially extended systems, and these are the questions we want to address. And so the solutions or the functions that we're looking at are, there's some quantity psi, which depends on x and t. And let's assume these oscillations arise in a Hopf bifurcation. Let's probably assume a supercritical Hopf bifurcation, although that's not essential at this point. Okay, so but if we have a Hopf bifurcation, then there's some small amplitude. So let's put an epsilon in front of it. And it oscillates in time with some frequency. Let's call it a Hopf frequency. And then, of course, there's the complex conjugate. And then there are higher order terms. And so the point we want to make now is that this amplitude, which we know can depend on some slow time, could also depend on a slow space. And we'd like to get an evolution equation for this complex amplitude as a function of space and time. So as before, we want to first get an idea of what kind of form that equation should have. What can we expect? And so, as I said, we want to assume a system that's reflection symmetric in space. And right now we're assuming it's just one-dimensional. So we assume a reflection symmetry and spatial translation symmetry. And actually also temporal translations, meaning the coefficients do not depend on time. It's not forced, right? Not one of these forced oscillators that we had before. Okay, so what do we learn from that? So let's first look at the reflections. If x goes to minus x, we need to see what the action is on our complex amplitude. So if x goes to minus x, well, it doesn't show up here at all, so that means there's no action on A induced. So it's actually a trivial action for A. Then we simply have A going to A. The only thing we conclude is that the slow variable should also flip sign. And so if the original system is spatial reflection symmetric, that reduced equation that we will get should also be even in space reflections. Okay. Then we have shifts in space. Well, since x doesn't show up in this exponential here at all, it's the same trivial action, so I can actually combine that together like that. And except here, then we know that the resulting equation must be invariant of x going to x plus delta x. So the coefficients should not depend on the slow variable. Okay. So, and the time translations, of course, they give us, like before, they give us a phase factor here. So we have A going to A times e to the I omega h delta t. And so that's, the equation has to be equivariant under this operation. But that's just like we had when there was no spatial variable. So that's why it's not surprising. Okay, so that means, how should we scale things? I've introduced an epsilon here, but we need to introduce scales for the time and for the space. And since we have that the only even derivative in this low variable x can show up because of reflection symmetry, but there's no reflection symmetry in time, so first order derivative can show up in time, and so therefore we expect there's d by dt, slow time, that's needs to be balanced with something like this. And so we introduce a slow time epsilon squared t and a slow variable x like epsilon x. And then the only equation that actually consistent with that is the following. So we have a second derivative with respect to x. Then of course we have the a itself, and we have a absolute value squared a. And we have coefficients. Now, since the reflection only generates a trivial action, we don't get a condition on the coefficients. Recall for the steady patterns, we had actually that the reflections in space required that the coefficients had to be real. That's not the case here, so we get actually general complex coefficients. So you could write it like this, dr plus I di, just to make it very explicit that these coefficients are complex. And then you have here, and let me put here a minus sign just because I'm imagining a supercritical bifurcation, and then the gr would be positive. So that's the equation we should expect. And if you go ahead and do the derivative, the derivation with a multi-scale and so on, you will actually get that equation. This equation has 6 parameters, which is a lot, but not all of them are actually relevant, so to speak, because we can rescale things. We have time to rescale, we have an amplitude to rescale, we have a space to rescale, so that will get rid of 3 coefficients. And we can multiply the overall equation with a factor. And so when everything is said and done, you can actually scale dr to 1. You can scale mu r to 1, and you can scale gr to 1, and you get then this following equation. You can do one more thing. I didn't say anything about mu I, but you recall we can get rid of this coefficient by making a transformation of a going to a times e to the I mu I t, slow t, right? This will remove that coefficient. And so that will do that also. And then when everything is said and done, we get the following nice equation. And I'm not going to introduce different variables for that. I just write it in the same things. So we have 1 plus IEB times dA by dx squared plus a minus 1 plus IC, a absolute value squared a. So that's the equation we get. And that's called the complex Ginzburg-Landau equation. For obvious reason, it looks like a Ginzburg-Landau equation, and we just say complex because the coefficients are complex, which makes a huge difference in what can go on. Okay, let me just make a couple of other comments, which are minor, but just to make sure we don't overlook them. So by having a plus 1 here, I made 2 assumptions. First, I made the assumption that mu r is positive. And so therefore, once I've written it in this way, I cannot tune the parameters anymore so that I would be below the half bifurcation. If you want to do that tuning, you just keep that parameter mu r. Similarly, by putting a minus 1 here, I've assumed that this half bifurcation is supercritical. So meaning the gr is positive. Okay. But that's an interesting enough case to just look at it by itself. And so let's just look at simple solutions. This is very similar to the before, but let's just see what they are. So we, of course, can get, again, making use of that special nonlinearity, we have solutions that go like a times a magnitude times e to the I qx plus I omega t. And when you do the plug it in, you get r squared is equal to 1 minus q squared, and omega is equal to, excuse me, minus c minus, no, not minus c, sorry. I wanted to dodge thinking, I don't want to do just copying, but that didn't work out so well. Minus c r squared minus bq squared. Okay, so what's the important thing to note here? Well, the frequency depends on the wave number, right? Which is quite common for waves, right? You expect the frequency to depend on the wave number. And it also depends on the amplitude of the wave, which is typical for nonlinear oscillators. Okay. And so the important coefficients are C and B, which actually characterize those dependencies. Okay, so now we have a nice equation, and we could further analyze it. You can actually do all kinds of analyses on this, so we will not dig into this. This is a very rich topic, and one could spend a lot of time with it. But let's now just focus on one aspect, because that's relatively easy for us because we've done a lot of legwork already. So let's again think that we have these oscillations, and they're not necessarily synchronous. So the different oscillators, if you want, at different locations are maybe out of phase. And we'd like to have a description for that phase, just like we had for the steady patterns, right? There we could get a description just for the position of the maxima, so to speak, the phase. And similar here, we'd like to have a description just in terms of the phase. And that will also, like in the case for the steady patterns, will give us a tool to at least extract one type of instability that the system can undergo. It could undergo more instabilities, but we capture one of them. And so let's do that. So let's recall for a moment, in the steady pattern case, we made a reduction to a phase equation, which was based on the observation that long wave modulations will be slow in time. And once you have a separation time scales, you can reduce the equation to a simpler equation. So similarly here, we would like to have some kind of slow dynamics. And it's again, just like in the steady pattern case, it arises from the fact that this oscillation breaks a continuous symmetry. Recall, for the steady patterns, the system was translation invariant in space, and the pattern broke that continuous symmetry. And that's how the slow evolution arose. Now here, this basic state that we're looking at, which is just this oscillation, does not break the spatial continuous symmetry. So why would there be slow evolution? Well, but it breaks the translation symmetry in time, right? So there's because we have no forcing on the system, there is a continuous translation in time, and the oscillations, of course, break that continuous symmetry. And so therefore, again, the same procedure will work, that we get an evolution for that phase, which is in this case actually a temporal phase. It tells us the phase of the oscillation and not the phase as in the location of a maximum of a pattern. Okay, so we only have these phase dynamics, and so, well, how should we write it? Let's see. Okay, from what I just said, that approach should be possible even if for a more general system that shows oscillations, right? It wouldn't have to be this weakly nonlinear Ginzburg-Landau framework. But just like in the case before, it's easier to work there. And so let's just to get a first idea of what's going on, let's analyze this equation in view of that slow dynamics of the phase. So to do that, we will introduce super slow scales. And so let me allow me to make these scales fast, so to speak. I mean, fast looking, because we'll introduce slower scales yet. So this will be a dt, and this will be d2a by dx squared. And as before, we rewrite this first in in magnitude and real imaginary part, right? So if I write a as r of x and t times e to the I phi of x and t, then I get equations for the magnitude and the phase. Let me just write them down. They're very similar to before. They have additional terms due to the fact that we have now the B and the C term, which have a big impact on the outcome. Let me just copy the equations down. So we have dr by dt is equal to, then there's a dr by dx squared. And then we get these other terms from the derivative from the exponent. So then minus r dx phi squared, now the new term minus b times 2 d phi by dx times dr by dx plus r d2 phi by dx squared, and then plus r minus r cubed. And then similarly we have d phi by dt. We have a new term with b, which has a 1 over r dr by dx squared minus d phi by dx quantity squared, and then plus 2 over r d phi by dx dr by dx, and then plus d2 phi by dx squared minus cr squared. Okay, so this is a little bit more complicated, but it's straightforward to obtain. So we want to have an equation just for this phase, and we want to in particular describe modulations of that phase. Okay, so the question is, what kind of equation should we expect? Well, when we did the analysis in the steady patterns, we did this WKBJ kind of approach, which was powerful because it generated a nonlinear phase equation, but it was somewhat involved. So right now, let me not do that here, although one could do the same thing here. Let's right now instead be more modest, so to speak, and say, well, let's assume we have, actually, let me assume we have homogeneous oscillations. So we are not looking at traveling waves. One can do it for traveling waves. We're not going to do it. We're looking at homogeneous oscillations, and then look only for small perturbations around it, small modulations. So we're not only saying they have to be long wave, but they also have to be small. And so let's write that down. So we're looking at small perturbations of the phase. And so we write the phase as, well, there's first, you get, when you look at the homogeneous solution and without modulation, the phase is oscillating. It actually goes like minus CT. That's this dependence of the oscillation frequency on the amplitude. And then we allow a modulation, and we're assuming that's small. So, and that small thing, then we introduce a capital phase, and that phase we assume varies only slowly in x and t. Well, if you make an ansatz like that, then of course the amplitude has to be modified too. So there are perturbations of the amplitude, so it will be plus epsilon times an r of x and t. But we actually don't know yet that power here. So let's just put here an alpha. We don't know what the scaling should be. And so we'll just start, and then as the need arises, we'll pick the alpha correspondingly. Okay, so the point is that we want to have an equation for this phase. And so that will arise essentially from this equation for the phase. And so what do we expect? Well, the first statement is that if you shift the phase of all the oscillators, you mean you shift everywhere by a fixed amount, nothing happens, as in the dynamics will not be changed. You don't get a restoring force, you don't get an advancing force. It just means everybody got advanced by that phase, and that's it. And so if you have an evolution equation for this capital phi, so we expect an equation that looks like this, equals, and there's some function f. And so in principle, if you wrote it down, you would imagine there's a phase phi, and then could depend on the gradient of phi, could depend on the second derivative on phi. I mean, could do more, whatever. And we know, however, that if you shift the phase is not changing its speed. You just advance the phase. So that means that this term cannot be there. F cannot depend explicitly on the phase itself. It can only depend on its gradients. Good. That's one less thing to worry about. So then we also said we have a spatial reflection symmetry, but no temporal reflection symmetry, which is sort of reflected explicitly here. A first order derivative in time, second order derivative in space. Same thing again here in that phase equation. We have second derivative, two derivatives. It's not the second derivative, but still two derivatives. So in other words, x to minus x leaves the right-hand side invariant, as it does to the left side. So therefore, we expect that this function f has to have, each term in the function f has to have an even number of derivatives. Can be first, but it has to be even number of d by dx. Okay, so then into leading order, we sure expect that we get a balance between the time derivative and the diffusive derivative. And so we expect that we should have t epsilon squared and x, not epsilon squared t, and x being epsilon x. So we have that diffusive scaling, and we're ready to roll. Okay, plug in. So let's see, let's analyze the terms that are there. So let's first note that r depends on x and t only through the little r. So there's an unknown factor of epsilon in front, but it's at least epsilon. Could be more, could be a higher power of epsilon, but it's at least epsilon. Then all the spatial derivatives are at order epsilon, and the time derivatives are order epsilon squared. So that means we have this term here is at least order epsilon cubed, as is this. This term here is there's epsilon from the phi, epsilon squared from the phi squared. This is actually order epsilon to the fourth. So maybe I just make a note. So let me just put sort of a little, this is, we know that's epsilon to the fourth. How about this guy? This guy is again epsilon, epsilon squared, epsilon cubed. This is at least epsilon, so this is bigger than 4, bigger or equal than 4. This guy here is epsilon, epsilon cubed. Well, this is epsilon cubed. And then, well, here, that's depends on alpha, right? So let me not write down anything. Then the d phi by dt, that's order epsilon cubed. What else do we see? This term has an epsilon here, two epsilons here. This is at least epsilon cubed. This is again epsilon to the fourth. Here we have again, well, it's the same term as that, so it's big, at least 4. And then finally we have this, this term is, what is that? That's 3. And the last term is alpha. Okay, so what do you see? Well, I guess we could write then, if we, just for completeness, we could write it down. R is alpha, so this is alpha plus 2. And this is also alpha plus 2. Okay, good. So, so the leading order, we simply get from the R equation only this term. Let's write that down. Order epsilon to the 0th. We get 0 is equal to R0 minus R0 cubed, and therefore R0 is simply 1. Well, R0 could be 0, but that's not an interesting solution. Okay, so R0 is 1. That's what we get from here. And from the phase equation, there's nothing there at order 1. Okay, we move right on. And then we see the first term actually that really shows up is order epsilon cubed. So that means alpha, let's pick alpha equals epsilon cubed. There's no need to have, alpha equals 3. There's no need to use a smaller one. So let's do that. Let's actually say alpha equals 3. And then we get the following equation. Well, first we should do the R equation first, right? So if alpha is equal to 3, then this term is 5, this term is 5. So these are completely negligible. This is negligible. This is also negligible. And so we have only, at cubic order, we have this term and whatever comes from here. Okay, let's write that down. We have minus b times r0 times the second derivative of phi. Okay, so we have 0 order epsilon cubed is equal to minus b r0 d phi by dx squared. And then we have plus little r minus 3r0 squared, little r. Okay, which we can simplify because r0 is 1, so this is simply minus b d2 phi dx squared minus 2 little r. Good. How about the phase? The phase equation, here we have a cubic term. This term is higher order. This is actually fourth, what is that? 2 plus 3 is fifth order. This fourth order, forget it, forget it. So you only have this guy and this guy. And so we get the equation d capital phi by d capital T is equal to the diffusive term d2 capital phi by dx squared minus c r squared. Well, the r squared gives us a 2r0 little r minus 2r0 times c little r. And so we simply need to solve for little r. And when we do that, we get the equation d phi by dt is equal to 1 plus bc d2 phi by dx squared. Okay, we have derived the equation for the phase, for small perturbations in the phase, and it's diffusive. Okay, that's not surprising in terms of the symmetries in time, space and time reflection symmetries. And we have a diffusion coefficient. This is our diffusion coefficient. And since we didn't allow any significant variations in the wave number, it's just a constant. Of course, if we had allowed variations in wave number, we would depend on the wave number. But we have a more modest approach right now, and so it's just a number. Okay. However, the interesting part here is that this number does depend on the coefficients of the Ginzburg-Landau equation, b and c. And so now we actually see that there's, if BC is bigger than minus 1, then D is positive, and its homogeneous oscillation is linearly stable. Okay. If you make a small perturbation, it will relax, so meaning the oscillators will eventually all be synchronized again. If you were to do, let me talk about that later. So let's now note down, if BC is smaller than minus 1, then D is actually negative, and the homogeneous oscillation is not stable. So you start with the homogeneous oscillation, make a small perturbation in the phase of the oscillators, and that perturbation will grow. What it will do, we don't know. We just know it will grow, and we need to investigate that. Let's just recall, in the steady patterns, we had a situation like that too, when depending on the wave number, the diffusion coefficient was positive or negative, and it went through 0 at the Eckhaus instability. And the simulations showed that when you moved across the Eckhaus instability, as in make the wave number too large, then the perturbations grow, and eventually actually the wave number changes in a phase slip, through a phase slip. And then you get back to a stable wave number. that actually tells us also that in the steady pattern case, at least for the real Ginzburg-Landau equation, there was always a range of wave numbers that were actually linearly stable. There was always an echo-stable range of wave numbers. So how is the situation here? Well, we don't know because we just picked the wave number 0, and now we would have to do the calculation for non-zero wave number. We'll not do that, not here. But one can do the same calculation when Q is not 0. And then one finds out, sort of, if I make a sketch, if BC is bigger than -1, you have, again, sort of a stable band of wave numbers. So, it looks sort of like that, some parabolic shape. And well, this is the wave number Q, and that's the parameter mu. Okay, right, the parameter mu, which actually in this approach that we've done here, we rescaled mu away to just being 1. So strictly speaking, that diagram here should be thought of only as, well, right here, where mu is equal to 1. But I want to draw it this way to make the similarity to the steady patterns more clear. But when you change mu, not mu, when you change BC, B or C, then this stable band changes. And when BC becomes smaller, goes closer to -1, it actually becomes narrower and becomes narrower. That's to be contrasted with, like in the real Ginzburg-Landau equation, there was no parameter that we could change to change the width of that stable band. Here, there is. And when BC is equal to -1, when BC is equal to -1, that stable band disappears, meaning there's no wave number left anymore for which the waves are linearly stable. So let me write that down, because that's really a very important and interesting result. When BC is smaller than -1, there are no stable, linearly stable, traveling waves of the form of this form psi goes like e to the I omega ht plus I qx, right? So just planar traveling waves. They are not stable for any wave number in that regime. This is called the Benjamin-Feir instability. It's just a word. I mean, Benjamin and Feir had a paper on it, and they identified that first, and so fine. It's also a sideband instability. In some sense, it's actually very similar to the Eckhaus instability, except that in the system, it can be there for all wave numbers. And that's when one talks about Benjamin-Feir, if that instability kills all the wave numbers. And what happens then, we don't know. Right? We can't speculate, well, maybe it adjusts and goes to another stable state, because we don't have any stable states that we can recognize, right? At least all the states that we can access, which is homogeneous oscillations or traveling waves, they're all linearly unstable. So that's a regime where one first would do some simulations. And then once you have simulations, then you can ask new questions, see, well, okay, this is what's happening. How can I get there? So we'll do some simulations next time, just to see that there's actually a whole zoo of behavior in that complex Ginzburg-Landau equation that is possible.